Welcome, everyone. My name is Mark Hughes, and I'll be your host today for a webinar that presents Joe Selvik and Duncan Lowder of FixtureFab. This webinar is presented by Advanced Assembly and Royal Circuit Solutions. If you have any questions or need technical assistance, please email mhughes@aapcb.com. This webinar is being recorded and slides will be available within the next 2 or 3 business days, and they will be found at aapcb.com/blog. Our previous webinars are available at either aapcb.com/blog or royalcircuits.com/blog. So if you'd like to check out some of our past webinars, visit us there. We put the slide decks on when we are able to. As we go through and you have questions, please ask them in the Q&A function down at the bottom of your screen. With that, let's bring in our 2 presenters today, Joe Selvik and Duncan Lowder. Joe and Duncan, nice to meet you guys. How's everything going today?
It's going great, Mark. Thanks for having us.
Yeah,
oh, no, the pleasure's all mine. Before we get going, can you guys tell us a little bit about yourselves? Maybe Duncan, we'll start with you.
Yeah, so my name's Duncan Lowder, and I'm the founder of FixtureFab. I've been a electrical or test engineer for the past 10 years or so at various consumer electronics companies, and I've always been super stoked on circuit board testing. So that's why we started FixtureFab.
Oh, cool. And do you have any projects that you're particularly proud of in your resume there?
I guess like the biggest things that I've done is I kind of implemented PCBA testing for a couple different companies that ended up manufacturing like 5 to 10 million products, which I thought was really cool.
Yeah.
So just being able to stand up a test line and like actually see it go into like full mass production was really, really fun.
Wow. Yeah, that's certainly better than my most recent accomplishment, which is eating a tube of Ritz crackers. Wow. And Joe, how about you? Tell us a little bit about yourself.
Yeah, so I went to the University of Minnesota for computer engineering, I think 7 years ago now. And then I've been mostly a software engineer ever since then for like various companies doing software quality. And then Duncan and I have always bonded over wanting to build our own company. And there was a nice fit with his fixture ideas. So recently I've been handling a lot of the sales, marketing, growth for FixtureFab too while we build our initial customer base.
All right. Do you have any hobbies outside of engineering that you enjoy?
I played competitive chess for 12 years through grade school. So that was really fun.
You're kidding.
Yeah.
Competitive chess. I have trouble with checkers. Really, I should be out there just, hitting rocks with hammers is my level of skill with that. But man, good for you. That's certainly a challenge. All right. Well, with that, gentlemen, I'm here to learn about test fixtures. Teach me everything there is to know.
Sounds good. So today we'll kind of go over like PCBA functional test fixtures and kind of like what they are and how you can build them. And then we'll also go through a demo of like how you can design a fixture using our automated design platform towards the end of the presentation. And this is kind of aimed towards any electrical or firmware engineer or basically any development engineer who's working on a hardware project and interested in implementing a test during the manufacturing process. So the typical PCB manufacturing process is kind of broken up into 3 different stages. There's the assembly state where you're placing the components on the circuit board and then soldering them onto it. Then that's followed by an inspection state where you'll actually use automated optical inspection and possibly automated X-ray inspection to verify that components are in the correct location. And to do this, those machines actually use computer vision and a reference to a golden board to make sure that everything's in the right spot. After inspecting that all of the components are in the right spot, you want to electrically verify that all of the component values and solder joints are connected. So for this, you can use both in-circuit testing and functional testing. In circuit testing, you can use either a flying probe machine where it has two needles that will actually go around and touch test points on the circuit board and take measurements between them. Or you can use an in-circuit test fixture where it will actually be a bed of nails and it will go into a fixture and perform the same type of testing. And then functional testing is when you actually apply power to the circuit board that you're testing, and then you functionally validate that everything works on it. So you'll validate that like a motor driver works or that your voltage rails are correct. So we'll be focusing on functional testing today. So what does a functional test actually do? For this, we're just using a SparkFun Redboard as an example. So this is an Arduino clone with like a couple different components on it. If we were to try and test this during manufacturing, we'd want to test that the voltage regulators on the board are outputting the correct voltage, that the processor can actually be programmed and run, and then that we can actually communicate with the processor over USB, since there's a USB to serial chip on it. And so whenever you implement a functional test, you're just looking at verifying that all of the functions of the circuit board actually work, and that you can then integrate it into the full product that you're building and everything will run correctly. A big thing to know with functional tests is that you're looking to just validate that it works. You're not looking to verify anything. So you don't really care about your test limits to, plus minus point something percent. You're fine if, you make measurements within a couple percent.
So it's just kind of go, no-go testing?
Yep, exactly. You're looking to just validate that it actually does what you want, and if there's any critical features that those are there.
So the SparkFun Redboard, would they have actually gone in with flying probes and done that here, or do you think they just kind of plugged it in?
On this one, I think they mostly just plugged it in. They definitely have some sort of test fixture, but there's just not very many test points on the circuit board, so it's not really aimed towards being tested by a flying probe or like a bed of nails fixture.
All right.
Yeah. And actually, yeah, we'll see this board a little bit later on, and we can explain the test points on the bottom of it. So the main reason for why you want to implement a functional test is to help you save time and money when it comes to scrapping bad circuit boards. So if you test the circuit board at the board level, then if it's failed, you can either rework the failed component or scrap the circuit board, and all you're out is a circuit board. If you wait until later in the process, like in this example, it's like the circuit board that goes into the iPhone. Like if that circuit board is assembled within the entire phone, when you get to the end of line tests and it fails, you then have to completely disassemble the phone, which I don't know if you've taken apart a cell phone, but it's just a ton of adhesive. It's hard, it takes a long time, and it's really expensive. So by implementing functional tests, you can identify these failures earlier and save you time and money by the end of the manufacturing process.
What's the, you said you did a thing with 5 or 10 million.
Mm-hmm.
What's the yield on that sort of thing? How many errors or what % errors do you tend to see?
Yeah, so your error rate will like decrease over time, or at least that's the goal. So like when we initially introduced the product, we were actually failing like pretty high. So we're about 30% of the boards would fail functional tests. And this was a combination of kind of fixture issues where there's like false failures from the test fixture, as well as the PCB manufacturer we were using didn't have their process very dialed. We're using a low-cost manufacturer over in China for this. And then as we kind of started producing more and more units, we were able to get it up and over like the 99% threshold eventually. And so ideally you're looking for like less than 1% fallout at this stage.
All right.
Yeah, and a lot of that like depends on the complexity of the board. Like if you have a processor with a ton of BGA pads on it, like you're gonna have, that's harder to assemble and you'll have more fallout. So to actually implement these test fixtures, it takes a wide array of engineering skills. To design the mechanical bed of nails fixture, you need to do a decent amount of mechanical engineering so that you know that all of your test probes are in the right spot, that you're pushing down on the PCB and aren't going to bend it. You need to apply some electrical engineering with connecting between the test points in the fixture and the instrumentation that will actually be making those measurements. You need to know what instrumentation you need to choose for what measurements you're taking. And then there's some software engineering involved where you want to write a automated test script that will run this test so that you don't need the test operator to actually do anything. So the standardized kind of functional test fixture approach is you'll have a bed of nails fixture that's manually wired. Typically, like you'll wire out from the test probe to either an interface plate or the actual instrumentation that you're using. Then the most common thing is to have like a rack of PXI test equipment. So this is like fairly expensive test equipment that you can purchase from like National Instruments or Keysight or various other vendors. And then most people use a combination of LabVIEW and test stand to develop the actual test scripts and run them in the factory.
How long does all that usually take to get set up?
It takes a pretty long time. So the fastest I've ever seen a fixture get turned around was about like 4 weeks. But it was pretty simple. And I've also seen them take up to like 6 to 7 months to deliver a complete one.
Wow. And it certainly looks expensive.
Yeah, definitely expensive. Most of the commercial vendors that I was getting quotes at, it would put functional test system costs around like $100,000 or so to contract all of it out.
Wow.
Yeah, expensive.
Yeah.
So, and a lot of my time was at like a consumer electronic company where we were building low cost like IoT devices, and we weren't able to spend $100,000 on a fixture and justify it. And so that was kind of what helped start me down this road to what we call now the Fixture Fab approach, where we're still using bed of nails testers, but we've kind of changed the other components to help decrease the cost of the system.
Well, I mean,
So,
if you don't mind me saying, where you got yourself into trouble was when you tried to justify spending $100,000.
Very true. If I had just spent it, probably would have been fine. So at FixtureFab, like we use INGAN test fixture bases. So it's a very simple, like a bed of nails fixture system. However, INGAN provides like very robust and fairly low cost test fixtures. And we're able to integrate the entire test system within the fixture base. So we'll actually put a computer in there as well as all the instrumentation that's needed to take the measurements. And we do this by designing a custom circuit board for each test fixture that solders to the test probes, as well as using some instrumentation from a company called Acroname, which actually slides directly into that circuit board. So that eliminates the need for having a complete external rack with a bunch of instrumentation in it. And then instead of paying thousands of dollars for licenses to test stand and LabVIEW, and the fact that neither Joe or I prefer to use graphical programming, we've implemented a like test framework based in Python that heavily leverages a bunch of open source libraries that are well documented. And so by moving here, we've been able to like eliminate costs and streamline our fixture designs. So how do you actually interface between a circuit board and a test fixture? And what does the fixture actually do? So the first part is like you make a measurement on a test, like on the device you're testing using a test point. And you interface to that test point using a Pogo pen, which is a spring-loaded pen. This is the bottom of the Artemis board, and you can see there's like various test points on it. So they would probably use these for programming the board during manufacturing using a bed of nails fixture, like a simple one. So the actual test fixture also consists of 2 different parts. So there's the test fixture base, and this can be reused from device to device. And this is where we build in the computer. And this acts as like a panini press to press the circuit board against the test probes. And then there's the interface cartridge, which is the part that's actually customized for the circuit board that you're testing. The cartridge consists of 3 different plates, and those are the plates that you actually need to customize for each different circuit board. The pressure plate will have pins in it that will push down against the circuit board that you're testing. the moving plate will support it from the bottom to prevent you from bending the device under test. And then the Pro plate is what will actually have all of the Pogo pins and receptacles mounted to it. So within our test fixture bases, we integrate a computer, usually an Intel NUC, as well as a USB hub, and then any power supplies that are needed by the fixture. And then for the interface cartridge, this is the part that actually gets customized. So we have the kind of green Pro plate. So that will have all of the holes machined into it for the various test probes. There's the test point carrier board underneath it. So that is a custom circuit board that will then interface all of these test probes to whatever instrumentation we're using. In this case, it's a acroname USB stem that we're using to control the entire fixture. And then on the top, there's the moving plate that's supporting the device that's being tested.
There's, if we can go back for a second, there's a lot of test probes there. How much force? I mean, each one of those is a little spring. When you add all that up, does it become a problem, or?
Yeah, it can become a problem. So it depends on exactly which test probe you're using, but the ones we use for the most part apply 1 Newton of force, like for each pin. And like this fixture, for example, has, I think, like 200 to 250 pins on it. So like that's a lot of force when you add it up. And specifically, like when you have a connector with a bunch of pins where you're probing off like every pin on that connector, like if you like I have a bunch of force just in that one corner of the circuit board and you aren't pushing down on it, it'll cause the circuit board to actually bend when it's put into the fixture. And that can cause a lot of issues with like actually causing failures on the circuit board that you're testing as you're testing it. So that's where the you need to actually do some mechanical analysis to make sure that you aren't bending your circuit board due to the forces involved.
And how do you do that? Like finite element analysis, or?
Yep, exactly. So you need to model what your test fixture is in CAD and then do some finite element analysis. And that's like one thing, like if it's a complicated fixture with a bunch of pins, like we will definitely do that. However, if it's really simple with not too many and it's low risk, then we'll usually skip that step.
Okay.
Here's kind of a closer look at that same interface cartridge just within the fixture. So the first picture is the complete fixture without a device under test in it. The middle picture is the moving plate. From here, you can see that the test probes are actually recessed a little bit from the plate. This is because you don't want the device you're testing to actually interface with any of the Pogo pins or instrumentation before you have it closed in the fixture. And then on the right side, that's what the fixture looks like. Or you can just see all of the Pogo pins kind of poking up through their holes. And so you can see there's a lot of them. On this test fixture, we're testing a kind of development board that had a socket for a device that had 3 like 50 pin 1.27 millimeter spacing connectors. So it was a lot of pins in a very small area. Lots of force.
Yeah.
Here's a look at the test point carrier board for that circuit board. Your obligatory botch wire from not doing a design review. And then this test fixture was just doing continuity checks for the most part. So we have a bunch of kind of multiplexers, and then the acroname module would actually control those and then take the measurements between 2 points. So this is just a custom circuit board, and it's much cleaner than having to manually wire to each one of those test probes and then run that to separate instrumentation. So instead of running, 250 wires, we just have one circuit board and it connects over USB and a power connector.
That still seems like a whole lot of pins in a very tiny area. Is that best practice, or is that just kind of what happened?
This is not best practice. It's just what happened on this board. So we had to deal with it.
Yeah.
And that's also why kind of design for test is really important as you're designing your circuit boards. If you go into the layout process, like knowing that you're going to use a bed of nails fixture, you can kind of follow a couple best practices to make it much easier to build a robust test fixture. For example, like using a test probe that's 75 mil or like 1.9 millimeter spacing is much more reliable than using a 50 mil or 1.27 millimeter spacing probe. And that's just because the probes are larger and more robust, and they don't fail as often. And so by keeping those ideas in mind as you're designing, you can make this test fixture process much better, and you'll end up with a more reliable fixture at the end. The last part that you need to customize of the test fixture is the pressure plate. And so this is the plate that actually pushes against the circuit board that you're testing, and it will push it against the test probes that are mounted into the probe plate. So just as an overview for like the systems that we actually deliver, we use Ingen test fixture bases. They're great. If you're looking at building your own test fixture, like I would highly recommend checking them out. Can't recommend them high enough. And then we use acroname MTM instrumentation as much as we can. So this allows us to integrate everything within the cartridge, as I mentioned, and it makes for a very clean test fixture. And then where FixtureFab specializes is we will implement the automated test script, as well as do the actual customization of the cartridges for whatever circuit board that you're testing. And where we are a little bit different from a typical test fixture house is that we spend a lot of time actually automating the design process, the mechanical design process of these cartridges. So how this process works is you'll take your ECAD file, which can be a test point list exported from Altium or Mentor Graphics, as well as we also support native CAD files from KiCad and Eagle. And once you upload this file, we'll identify the test point locations as well as mounting holes and some other features. You can then configure the test fixture. So enable and disable whichever test probes that you actually want to use, add guide pins and pressure pins, and then you can actually view a 3D render of the test fixture that allows you to move around the device you're testing so that it's located in the spot you want in the fixture. After you've done all of the kind of configuration and figuring out where you want the dot located, you can then generate a design file package. And then this you can either purchase from us to fabricate this picture yourself, or we can also sell you a complete machined and assembled test fixture.
So going back to the ECAD files, the EDA software files for a moment, is it only those particular software programs, or if I have something else that can export to one of those, I can still use your service?
If it can export to one of those, you can still use our service. You would just want to like validate that the export was valid.
And are those just the Gerbers, the 274Xs, or?
Yeah,
what
exactly.
Class? Okay.
274X. Kind of our like a preferred method right now is to actually use a test point list, and we have a template that you can fill out. And the biggest reason for this is to force you to actually go through the design process with your head, or the kind of like figuring out what you would like to test and what test points you actually need. So we'll kind of walk through that process here during the demo. And then for KiCad and Eagle's like files, the upload works great. However, with the Gerbers, we don't get net information from it. So you end up with a list of test points, but we don't know what net or designator there actually are. So you have to go through and manually look at their coordinates. So, you know, KiCad and Eagle are great if you design using those or can get your design file into that format. But for the most part, we've been recommending using the test point list. So one great part of automating the design of these fixtures is that we started applying it to development fixtures as well, instead of just production fixtures. So these are low-cost fixtures that you can easily 3D print or laser cut and use them throughout the development process. One of the companies I'd worked at previously, we were manually designing these like laser cut or CNC machined fixtures that we would use to help develop our PCBA functional tests before we actually had real fixtures available for us. And it just allowed us to like test various circuit boards and it was much easier to develop our test scripts. And as we were doing that, the firmware engineers at the company started seeing these fixtures and wanted them as well. And what happened was, like, it helped them kind of program and develop on various different devices, like, so much faster that they were saving about 5 hours a week from just having one of these fixtures around. And so we've started automating the design of these, because you can actually get a laser cut fixture within a week, and we're trying to decrease that lead time even more. And it just helps your development cycle as you're either developing the hardware or creating a test script. So we'll kind of walk through a little demo design right now using a circuit board that was made for the Teach Me PCB class.
Yeah, for those of you who don't know, and I don't see that George has joined us, Advanced Assembly, Royal Circuits, DigiKey, Altium, a lot of people have gotten together, and we're hosting a free PCB web design or PCB design course over at teachmepcb.com. The first cohort is finishing up now, but one of the participants, George Garcia, who works for Autodesk, made a board for us, and that's what we're looking at here. He's in a meeting right now, but hopefully he'll join us here pretty soon, and we'll have him tell you a little bit more about his design. Sorry, go ahead.
Yeah, so this is the board that George designed. So we're going to develop a very simple development fixture for it. This will be used for programming the board. So the test points we'll need for this fixture are located down here in the bottom right. So these will be used to program one of the processors, as well as a couple of test points up here in the top left, or middle left, which will be used to program the other processor. There's also like a power test point and a ground test point down here. So I've already gone through and done the work of creating a test point list. So this was done by going to the ECAD file, like zooming in on whichever test point we needed, and then just selecting it, which, maybe I'll figure out how to do. There we go. And then from here, you can get the coordinates of that test pad. I am all about millimeters, so I do all of my measurements in millimeters. Yeah, but there we can see. So, 59.309 and 38.481. So you can manually go through and identify exactly where each test point is, and then add those locations to this Google Sheet. And we have a template that you can fill out to use with our platform. After that, you can download the CSV of the sheet, and then we can move over to FixtureFab to actually do the design process. So from FixtureFab.com, you'll need to create an account before you can upload a project. But to create a project, you just need to enter a project name. So we'll call this badge the Teach Me PCB badge programming fixture. We'll leave the default PCB thickness, and then we will select our test point list that we created. So after this, you can create the project. This is, we will then kind of upload or identify all of the test points on that circuit board. You can select from a couple different test fixture types that we currently support. There's this toggle clamp fixture, which is 3D printable. A couple InGen cartridges that are supported for production fixtures. And then we'll use this Dev 260 laser cut fixture for this one. So from here, you can now configure the various test point settings. So for each test point, you'll need to select a receptacle and test probe type. We currently only support ones that we have in stock. However, we're working on increasing the numbers or the part numbers that we have supported. And then you also want to add all of your kind of guide pins and pressure pins. So for guide pins, there's a couple different ways to go about this. The ideal way is to use a what's called a spring pin, and that can be used with a mounting hole, and it will help locate your PCB wherever you want. And then it will also like spring back and forth as the PCB is pressed into the fixture. Since this circuit board design doesn't have any mounting holes on it, we'll actually use a couple of dowel pins. And the easiest way to find locations for like your guide pins is to look at your electronic design file and then see like, how can we actually locate it? So for this, I'm going to use 4 3mm dowel pins, and we'll locate them kind of by the robot's neck as well as down by its legs. And so this will like give us both like vertical positioning as well as horizontal. And then to add the actual pins, I found that I just add them to a layer with an eagle, and then you can like kind of create a circle and then set its diameter. So since I'm using a 3mm pin, we'll use a radius of 1.5 millimeters. And then you can then kind of move this around until you find the location that would work.
How accurate do you have to be with that location?
So you want to be within about, like, I'd say like 0.1 to 0.2 millimeters away from the board. Like the cool thing with dowel pins is you can bend them a little bit, but you really want them to be straight. So you don't want it to be like exactly on the board edge, but you want to be about like 1/10 of a millimeter away. And this also depends on the diameter of the test points that you're using. The larger diameter of the test point, the larger tolerances you have in positioning. So for properties. There we go.
Control Z, Control Z.
Yeah. So for this guide pin, it has a position of 23.9 by 31.3. So if we go back to FixtureFab, we can do add a new guide pin, give this a name, coordinate, and then the diameter you can leave blank, and we'll want this in the probe plate, and we'll choose a 3mm dowel pin. So from there, like you can save it or add additional pins. For pressure pins, you want to add those in a similar way. And with these, you can just kind of move the pressure pins we have a 3mm tip. So you can just move this around, or the circle around, and find the locations across the circuit board where you actually want to push down on it. We won't do that right now, but I have a completed project over here where we added.
Cheater.
Yep. So here, this has all of the guide pins. So we have 4 dowel pins used to locate the robot, as well as 4 spring pins, which actually have plastic tips on them and are used underneath this board to help even it out, since the Pogo pins we're using are only down here and here. If we were to only use the Pogo pins to like help like provide leveling of this circuit board, it would tip, since there's nothing up here to apply pressure to the circuit board. And then we added 5 pressure pins at various locations around the circuit board to push down across the entire thing evenly. So after you add all of the features that you need for the circuit board, you can then view a 3D render. From here, it will default to like the orientation of the board in your CAD software, as well as it will just center it within the test fixture. From there, like depending on the size of the board, you might need to change the orientation, and then you can also change like the actual location of the device. So here's a 3D render of what the test fixture will actually look like. From here, we can actually see that we have the 6 pins down here, the 6 Pogo pins that correspond to these 6 test points down here in the bottom of the board. And then there's the 4 dowel pins that are used to locate the actual robot. And then these white pins are the pressure pins that will actually push down against the robot. From this view, it looks like we're about centered. So we can actually just say that we're done with designing this test fixture and hit the generate fixture design. From here, this will actually create the design package, and you can then go on to purchase it from us as a download or purchase a complete fixture from us.
And I can also just say, hey, Duncan, I got a board, make me happy, right?
Yep, exactly. Yeah. If you have a board and you just want a test fixture, you can just send us an email as well, and we can work out a quote and design a test fixture for you. Let's see here. I'm going to stop sharing for a second because we actually have a demo fixture here. So this doesn't have the Teach Me PCB badge in it. I wasn't able to get that built in time.
That's
but
okay.
This is a development fixture for a small SparkFun like USB-C power delivery board. So with this, this board has 4 different holes that we're using to locate it. And then it has a bunch of different Pogo pins that are used to configure and then test it. Let's see if you can get a better shot of that.
Yeah, you can see that.
Yeah. So to put the board into the fixture, just put it in the right direction. And then you can kind of close the top, latch it down. And then from here, we actually have some instrumentation and a breadboard. And this is used to actually interface with the Pogo pins. For these simple development fixtures, you can actually just use like low-cost like jumper wires and connect them, like slide them onto the end of the test probe. So it's a great way to like just prototype fixtures super quick. And then all this does is configure the board using I²C. And then we validate the voltage output using an analog to digital converter that's on this USB host adapter that we're using. Yeah. So that's like the big thing about these fixtures is like we can get these like shipped to you within about like 4 to 5 days, which allows you to like have an actual fixture to develop with. And we found them to be like very helpful, like either developing test scripts or developing firmware, because it allows you to just throw a new device in. And if you're developing like a small IoT product or something where the circuit boards are really tiny and you don't have space for a programmer connector or like a tag connect connector, then you can just have a couple of test points on it and you can use those for your actual firmware debugging and development versus having to like, you know, add a connector to your circuit board that takes up a lot of space.
Very cool.
Yeah.
You've been very, very quiet over there, Joe.
Yep, I have been.
All right, so we do have a couple questions, and now's a great time to ask questions if you haven't asked them already. First one was, do you perform the stress analysis yourselves? So this is back to the mechanical, the FEA, or do you have a provider?
We've typically been doing it ourselves. However, we're looking at ways to make it faster to get results from that. For us, like we'll take our kind of our design from FixtureFab and then import it into either SolidWorks or Fusion 360 and then perform analysis within there.
Okay, so hopefully that answers your question there, anonymous attendee. We do have a question. Do you accept OBD++ files?
Not yet. It's on the list of like supported files. We're definitely moving towards using like or supporting like OBD++ as well as IPC 2581, I believe.
Something like, I don't, there's a lot of IPC standards, man. I don't.
Yeah, but like our goal is to kind of support the major CAD formats, and ODB++ includes everything we need as well as the IPC standard.
Yeah. One thing I would add to that for this particular user, Royal Circuits, you know, we get thousands upon thousands upon thousands of files a year. 98% of them are Gerbers. One of the reasons that these other formats haven't caught on, you know, the IPC 70, is it 7581 or whatever it is? Yeah. Gerber works. It's worked for decades and it provides plenty of information. So there's not a whole lot of motivation for people to move away from it. There's not a whole lot of motivation for cam houses to move away from it. So even though they can support it, they just don't. ODB++ is a good thing though. So might be something to add to the roadmap there. All right, we've got somebody. Could you use a position report to get your test point locations automatically? They should show up as a component even though they are not populated.
Yeah.
So, yeah.
A position report, yeah, that would be great.
Yeah. So XYRS potentially could have that information. It shouldn't even be that much work to write a quick Python script or just use a regular expression to, find the test point apertures and then pull them out of the Gerbers for this particular user. So yeah, if you have a bunch of points, if all of your test points are the same size, they're all going to show up in your Gerber file as the same aperture. And then you just need to go look at, when that aperture is referenced, and you'll get your list of XYs. So yeah, you could do that. Sorry, I probably should have given that question to you guys.
No, I really like the idea of using a position report. We're always looking for better ways to implement this. So yeah, send us an email. We'll talk.
That is actually one of the members of the Teach Me PCB course who asked that one. And he's the one that I put you guys in contact with.
Oh, Jesse. Yep. I need to get back to you.
Yeah, he's a good guy. I really like him. Can you ballpark, if you're comfortable doing this on the air? If not, that's okay too. But can you kind of ballpark prices?
Yeah. So the design package for the laser cut fixture is $100, and then for a machine fixture, they start at $300. So it's like a $300 base price, and then depending on the number of test probes and guide pins and stuff like that, the price will increase.
So in terms of electrical engineering cost structures, it's free. Yeah. It's really what it comes down to. Question is, the Pogo pins, do they generate interference when testing and validating high-speed signals?
So yes, they do. They do add some parasitics to whatever signals you're measuring. However, it depends like how high speed you're actually looking at. If you're looking at, measuring really high speed connectors, then you can use different types of test points and probes that enable you to actually, make those measurements. But we've had luck using just Pogo pins for anything up to even like USB-C and MIPI signals. However, if you're trying to do like signal integrity testing or anything like that, you'll definitely want to look for a different method.
Yeah, you'd want a coax or something along those. But most of us aren't doing that type of thing, so it's probably not a problem. Comment says, according to our PCB suppliers, OBD++ is preferred to Gerbers as it conveys more information in it and intent, not data. All of our seems required for denies review. Yes. Okay. So I should clarify. Royal circuits, we like the ODB++ as well. Definitely do. What I'm saying is that's not what we're getting from our customers. It's not that we're requiring Gerbers from our customers. That's what they're supplying to us. So my comment isn't that Gerbers are better than ODB++. And if I said that, I was completely mistaken. What I'm saying is we're getting Gerbers. Okay. But ODB++ would be preferred over just the raw Gerbers. For boards without test points, is it recommended to probe the pins on the bottom of the through-hole connectors on the board for a bed of nails fixture?
I would say yes. So like if you don't have test points, but you have through-hole connectors, then you can actually use like a cup style probe, and it interfaces with the bottom of connectors like great. It's a great method for probing those connectors. You can also get like side actuation mechanisms, which will actually plug into the connector depending on the connector type. And those can work well as well. However, they definitely add costs and complexity to the fixture. So most of the time, if it's like a large spacing on that connector, like 100 mils or even 50 mils, then I would go to probe it on the bottom.
Okay. This is one in chat, but I'm going to pull it in anyway. Is there any solution for pads on the edge? I'm guessing they're thinking things like castellated vias,
Okay.
that sort of thing is my best guess.
Yeah. So with like castellated vias or something like that, you can probe on it. We've had some issues, like the biggest issue is with like alignment, because as you have like the test probes come up, and if you only have like a half hemisphere to probe, like sometimes the board will just get pushed away. So if you have mounting holes or something that can definitely locate it in the right spot, you can get a probe tip that will actually work well on those. Our favorite, like if there are castellated vias, our favorite method of doing that is to go to the method where you have like the castellation as well as the through hole, like right next to it in the pad. And then we just probe onto the through hole part.
Yeah, it might also be possible to create a small toggle or a small cam that pushes the probes in from the side. But man, I don't know, you're asking for trouble.
Yeah, the side one, I've built a couple like that, and like, yes, they do work, but I know, they aren't very reliable. Like,
Yeah,
you end up with false failures.
yeah, and that's no good. Okay, you may or may not be able to answer this one. Have you looked at integrating your fixture generation tool with the production line tool test platform from Blue Clover devices? Are you familiar with Blue Clover?
We recently became aware of Blue Clover, and they have a really cool implementation for ICT. We haven't talked with them yet, but it's definitely something that we'd be interested in integrating our fixture with.
All right. Do we have any other questions out there for Duncan, or maybe something for Joe? Joe's been kind of left out of all of this.
It's easier with just one main point for the presentation.
Okay, well, with that, gentlemen, that certainly looks exciting. Very cool stuff, and it seems affordable and a whole lot of fun. How do you keep abreast of all of the changes in the test fixture industry? Or, if it's something that I want to learn more about, do you have any resources I can read or any suggestions?
Yeah, so we have a blog where we've been adding a lot of articles in regards to like how to design test fixtures and kind of like our methodology for it, which you can find at FixtureFab.com/TFG. We're calling it the test fixture guide, so we're building it out, and our goal is to like keep adding more resources to kind of help people learn how to do functional testing. From my experience, like there is some resources out there, but there's nothing that really goes into the technical details on actually implementing tests. Another interesting spot to look for resources is from SparkFun, actually. Within their blog, there's a couple of articles that they've released on how they do production testing. The latest one, I think, was on their test device called like the Flying Jalapeno or something similar to that, where they actually go into like how to test for short circuits and a couple other methods that they use. That's pretty interesting. And then there's also information from a couple of the larger test houses like Circuit Check as well.
All right, we did get a late question here. How do you deal with bent Pogo pins? Are pins soldered in place, or do you use the barrel holders for the pins?
So we use the barrel holders or receptacles for all of our pins. I didn't initially when I first started building these fixtures, and then you break a pin and it turns into a whole ordeal desoldering the pin and getting a new one back in. So I would recommend like the receptacles add a little bit of cost to a test fixture, but they're so worth it if you're designing your own. Like definitely use test probe receptacles.
Yeah, and the Pogo pins don't last forever, do they?
No, they don't. Most again, it depends on exactly what Pogo pin you're using, but they rate their lives in hundreds of thousands of cycles, and realistically, I see anywhere from 10,000 to 100,000 units depending on the fixture.
All right. Well, with that, it's certainly been educational, and I want to thank you both for your time. Your website is FixtureFab, FixturFab.com. No, there's no E. Just visit it, check it out, play around with the software, see what happens. Maybe you'll find that you can integrate it into your next design. Your time's valuable, right? So if I don't know what you make in your engineering jobs these days, $60, $100 an hour, more or less, depending on what you're doing. But you figure if you've got 30 boards and you're spending 30 hours of your time programming them, you're wasting money by not getting a test fixture from somebody or making your own or something along those lines. So look at the, you know, the cost benefit analysis and see if it makes sense for you. If you have any questions, you can reach me at mhughes@aapcb.com. Duncan, Joe, any last thoughts?
No, thank you for having us. We enjoyed this. It's great.
Oh, it was my pleasure. All right, everyone, have a great rest of the day, and we'll let you know when we're doing our next webinar. We're not doing them every week anymore, so have a great rest of the week and a wonderful weekend. Be safe. Bye, everyone.